All right, so yesterday we were discussing about the velocity reference model. That's where we were talking about. So we were looking at low pass filter based guidance, and particularly we were interested in the velocity reference model. And we were observing that this is a representative of a spring mass damper system, which is what we were using for our guidance purposes in order to generate a feasible trajectory for our vehicle. So you would have a similar sort of a what you call a similar sort of a filter for each of the different things which you want to control. So if you have a 3 degree of freedom system, you might have one for the velocities in surge and sway, or in the north and the east, and then the heading rate could be one another. So for each of them, you will have a low pass filter which you can tune in order to essentially get the desired trajectories out, which can then be given to your control system, and the control system will try to achieve those desired trajectories. So please notice here that we are actually saying that in the big scheme of things. So let me try to see if I can put a slide in front of this. Okay, so usually you will have a guidance system. Then you will have a control system. And then you'll have the plant. Then you'll have the navigation system. And the idea is that the output of the plant is measured by the navigation system. And in the navigation system, we may be adding some noise which might be coming in. And this output goes as a feedback and gets added to the reference signal from the guidance system, and that is the input to your control system, and that control system now controls the plant. All right, so typically for a plant you might have other things which might be coming in, so these are called disturbances. Okay, or unmodeled dynamics. Okay, so for our case, if we want to understand what is going on, we would call this plant as our ship vehicle, whose dynamics we are trying to kind of govern. Typically, we will try to use a modeling system where we might want to simulate the motions of the vessel in order to test a control system. But the other approach might be that I might actually deploy on a real vehicle. Then I don't need to do any computation in the plant part. Physics of the world gives me what the output of the plant looks like. Right? So motion of the craft comes as an output from the actual motion of the scaled model which we might be looking at. The sensors on it form the navigation system, which are measuring the different inputs, which might be like what is the position, what is the yaw rate, what is the yaw angle, and these are the things which we are measuring. Okay, that is what this navigation system is doing. It's trying to measure these inputs and provides the output, which is usually the state vector. So you try to estimate the entire state vector using a few inputs that you measure. So for example, I might be measuring, let us say, accelerations, velocities, and let's say it may not be velocities. I may measure angular velocity, and maybe I can measure positions using GPS. But with this, I try to estimate my complete state vector, which will include velocities, accelerations, yaw angles, all the different Euler angles and everything, right? So that would be my complete state vector, which I provided, which we generally denote as x hat, which means that it's an estimated value of the state which we are trying to govern from the measurements which we obtained. And that state is given as an output which gets added to the reference signal which we are providing from the guidance system. So let's say that is the reference signal plus x hat, and that becomes the error. So we take r minus x hat, that becomes the error, which is fed into the control system. Based on the error, the control system takes an action in order to figure out what is the actuation input which I need to provide to my plan, and then the control plan basically starts to do an action, and its output is the actual output of the plan. We can't measure x, so we only measure a portion of x. We try to reconstruct x, add it to our reference signal, find the error, feed it to our control system drives our plan, and this process keeps looping around. Okay, that's what is a typical control system looking like. So we are presently talking about the so-called guidance system, right? This is what is telling us how should I find this value of r, or that reference signal, or which we call the desired trajectory in this case, because we are currently talking about trajectory tracking. So far we have been looking at trajectory tracking problems in which we would assume that this r should have the so-called desired trajectory it should give us. Okay, so therefore when we are looking at the low pass filters for each of them, we will be having one for each of those mechanisms for which we want to drive the value. So we may have one for x, y, and psi, or we may have, if it's a velocity reference model, we may have one for the surge, sway, and the yaw rate, things like that. Okay. All right, at least the idea here is that what we are doing here is it's a second order system, and we talked about this idea yesterday that we can control the damping ratio and the natural frequency of the system in order to tune the shape of the filter, how it should be and what characteristics it should have. We want to figure that out, or we want to tune that as a control designer as to what should be the so-called feasible trajectories which should come as an output. So if we have n degrees of freedom, we will have n different damping ratios and different natural frequencies to tune, and we might want to put all of them together in a one single matrix equation for convenience sake. So that's what we are doing here. So what we are doing is we are putting together a second order matrix differential equation where we are not just taking each of the individual components individually considered, but we are pooling them all together into a matrix form of a system. Okay, so here we have our desired velocity vector differentiated twice, plus 2 times a damping matrix times the natural frequency matrix times the velocity vector's derivative plus omega square times Vd is equal to omega square times Rd. Only thing is, each of them had individual components. Now we are putting them all together. So notice that we previously had this definition as VDI, right? So if I were to look at the so-called vector Vd, it's nothing but a combination of Vd1, Vd2, so on up to Vdn, if assuming that there are n degrees of freedom in the system. Okay, so it's just a combination or concatenation of everything together. And you'll see that these damping matrices and the natural frequency matrices are also diagonal matrices which are inculcating the effect of tuning these different values. Now one might argue that why not I have this matrix as a full matrix and I can tune more, I have more parameters to play with. But for typical control operations, it makes sense to look at the damping modes individually, because we want to kind of look at each of them individually and want to combine them together. Yes, you could put a coupled mode also as there, or a coupled damping also as a part of the process, but usually the coupling is not quite strong, or at least when we are interested in the guidance system, we are not really worried about the coupling here. So it makes sense to tune it. It makes more intuitive sense when tuning that, okay, I want to add more damping into search, or I want to add more damping into yaw. I can be directly adding the damping rather than saying, I'll add damping into yaw, but through search. That is a little tricky, right? Not that it can't be done. It's a little, uh, it's not so easy or straightforward to grasp and understand when you're doing the tuning. Okay, so in a state space representation, so this so-called second order differential equation in matrix form, I can write it down in a state space form where I define this xd vector as a concatenation of vd and vd dot. So then I can write xd dot is equal to some matrix ad times xd plus a matrix bd times rb, where rb is my actual input, which is coming either from joystick commands or keyboard commands or some other mechanism which we are feeding into the to the guidance system, which is the input to the guidance system. And the output of the guidance system should be a so-called trajectory which comes out, a desired trajectory, which then we pass on to our control system. And here we are assuming that the control system is doing its thing and is able to track it properly. At a later time, we will look closely at control system to figure out what exactly is happening specifically with the control system. Is everybody with me so far? Yes? All right. Okay. So in which case, when you do this state space transformation, you can see that this so-called big matrix AD is a concatenation of 4 submatrices with zeros on the top left corner, identity on the top right corner, and then you have minus omega square and 2 delta times omega. This is not a very difficult transformation to look at. I leave it as an exercise for you to see it. If you can see it for a simple scalar valued system, it's not very difficult to see that the same holds for the vector valued system as well. Okay. All right, so the step input will result in a, okay, so if you look back at this system, so suppose I give a step input in this RB, which means that the values were 0 and then they became some constant value at time t equal to 0 and I held them at a constant value. Then eventually what will happen is over time, what do I observe? It might be better to actually observe from this equation. So I'm putting this as a step input. Okay. If there is sufficient damping in the system, over time, what will happen? What will happen to V double dot?
Be 0, right?
It will be 0. Similarly, V dot will also be 0. So what will we be left with?
Constant value VD.
VD will be equal to what?
RB, right?
RB. So whatever input I gave to the system, that is what should become the so-called desired trajectory as time tends to infinity. Okay, so that's what we are trying to say. So the low-pass filter is designed, or its gains are designed in such a manner such that as I give a step input in RB will result in a step input in VD dot. Sorry, in VD. Okay, so when I say limit t tends to infinity VD, I'll see that that should converge to RB. There is a mistake here. There should be no dot here. That's a mistake. Wait a minute. Wait a minute. Wait a minute. Wait a minute. No, no, no. That's not a mistake. Yeah, that's not a mistake. Okay. Okay, that's not a mistake. Sorry. Let me tell you what that means. Okay, so when I put RB as a unit value, you will see that this B matrix, which is coming out, is having a structure which looks like this. Okay, so when I provide a step input in RB, B times RB will be the so-called step which should be transferred to the state immediately, isn't it? So when I apply a step input in RB, at that particular instant, when the step is applied, that step will result in which quantity in XD?
VD dot.
It will be changing VD dot. Is everybody making sense? The VD dot will be experiencing a step input, which will cause VD to slowly vary and in a steady state value reach RB. As time tends to infinity, VD will reach RB, but at the moment the step is applied, the step will first get transferred to VD dot. Is everybody understanding? Is everybody with me here? I'm seeing a few blank faces.
So VD will gradually increase to RB, not as a step input, but gradually increase.
Correct. VD will gradually reach RB over time as time tends to infinity. But the moment I apply the input, first thing what will happen is the VD dot will experience the jump. But VD will not experience the jump. So that's why it is a low pass filter. All these fluctuations, sudden fluctuations which I am giving to the system, they do not get transferred to VD directly. They are insulated by it because of this so-called step, which is first coming to VD dot, and then VD dot has to slowly result in a change in VD. Is everybody following me? I'm seeing a few blank faces. Tell me now.
Sir, can you explain it again?
Okay, all right. So see, when I am multiplying BD times RB, right? I'll get zeros on the top and then I'll get omega square times RB at the bottom, correct? Basically, I'm doing this times RB, right? Is that making sense, Anand? When I do this matrix multiplication, what will I get?
Omega square RB.
The top half will be zeros, right? Because I'm simply
Yes.
multiplying by zeros. It's only the bottom half of the equation which will have some values in it. Correct? So when I have some values in there, what mode is it affecting? It's actually affecting the bottom half of this XD vector, right?
Yes.
Is that making sense? In
Yes.
some sense, I can write this XT dot as VD dot and VD double dot. That is equal to AD times VD and VD dot. Okay, plus I have 0 and omega square times RB. Yes. So when I apply a so-called step input in RB, I'm actually affecting a major change here.
Yes.
That making sense? Actually, I'm actually causing that to be the acceleration. In fact, I was probably even wrong when I said it directly affecting the velocity. It's actually affecting the acceleration, which cascades into the velocity, which cascades further into the position. Okay. Because this is a velocity reference model, we are taking the velocity's derivative is taking the direct hit when I apply a step input.
Yes.
Everybody following me? Aditya, yes?
Yes, sir.
Okay.
So that step input effect would be given to VD double dot.
It will be given to VD double dot.
And that will gradually affect VD dot, and that will
Correct. And then that would gradually go back and affect VD. So it's not even acceleration, it is the so-called what we call as the jerk, which is the derivative of the acceleration. That is getting the step input affected. That is then cascadingly down affecting VD dot, which cascadingly down is affecting VD. Okay. In the steady state condition, VD will reach the value of RB which I am providing. The desired trajectory will reach the reference value which I am giving. But initially when I apply it, it will first affect a change in VD double dot. Okay. That is why it will result in a slowly varying VD. Otherwise, if this integration functionality was not there, if this so-called second order system was not there, and I was directly just giving it, then the step input would reflect in a step input in the VD. If I did not have a low pass filter but a direct filter, whatever comes I just pass it on. Then I would have seen that whatever input I give, give a step input, the step input would be directly passed on. Now what is happening, if I give a step input, it will slowly transition my VD from the existing value to the new value which is equal to RB as time tends to infinity. Okay, all right. So in fact, this is a mistake here that this should be VD double dot. It will result in a step input in VD double dot. Okay, so that is what is a velocity reference model. So notice that here we are actually taking the desired velocities as an input function of the so-called joystick command or the so-called keyboard input which we are getting. But we could also define a guidance system which is taking as an input and trying to directly govern the positions and the orientation rather than just the velocities. I may also want to have a guidance system which can directly try to guide my position tracking rather than just the velocity tracking. So the previous one which we looked at is only giving me the desired velocities. It doesn't tell me anything about the desired position. I have to integrate those velocities in order to get the position. Correct? But rather, I could also have a guidance system which is directly giving me which is focusing purely on the positions directly. Is that making sense? Yes, no?
Yes, sir.
Yes? All right. So when we come to the so-called attitude and position reference models, we typically choose this to be a third order model. Okay. So what we are doing is we are saying that, okay, we want this not to be a second order model, but a cascaded third order model. Velocity is a second order model. So the position should effectively be another integration factor along with it. So it should be a so-called third order model. And we can define a third order model as a cascade of two filters. One first order filter coupled with a spring mass damper system. Spring mass damper system we are choosing because we are very comfortable with tuning the spring mass damper system. I could have combined the two together and said I'll just directly tune a third order system as well. But since we are comfortable with tuning spring mass damper systems, we may want to cascade it as a one first order filter put in together with a second order spring mass damper system combined together to give me a so-called third order system. Everybody following me? Okay. All right. Okay, so you will see here that in this case, I may be choosing a first order filter of the form as 1 divided by 1 plus Ti times S as the so-called transfer function for the first order low pass filter. And that is again cascaded together with the previously seen second order spring mass damper system which we saw before. If I multiply these two together, and typically if I choose Ti to be 1 by omega Ni, 1 by the natural frequency of the spring mass damper system, I can write this down as a complete third order filter by expanding out the expression, and you'll see that this is now relating to a third order system. Now, just as before, we will have a third order system for each of the different things. So for example, if you are looking at a search sway and yaw model, I might be looking at the position in X, position in Y, and the yaw angle. For each one of them, I'll be having a third order filter of its own in order to govern the dynamics or to find out what is the desired trajectories. So in that case, I can combine them again in a matrix formulation as I have seen before. And you will see that in this case, we are simply replacing this wherever I'm seeing zeta, I'm replacing with the damping matrix, a diagonal damping matrix. And wherever I'm seeing omega, I'm replacing that with the diagonal matrix of the natural frequencies. Same process as before, absolutely no difference. Only thing is, this is now a third order system. Okay. And if I put it back in the state space representation form, again you will see that the effect is the same. So now I have three things in my xd vector, which will be the eta desired dot, eta desired double dot. Okay, and again I can formulate this so-called AD and BD matrices, and a step input in Rn will now result a step input in Rn. Okay, that will result in the third quantity's derivative. So eta d taken the third derivative will be resulting in the step. Okay, and I think that's what I mentioned here. It will result in a step in eta 3b. So previously I had made a mistake that I have missed that dot there. So please make sure to put that dot back in there. Okay. All right. So the idea here is that eta, the third derivative of eta d, will cascade into the second derivative of eta d, will cascade into the first derivative, that will cascade further into eta d, which will be progressively more and more smooth because I am taking basically an integrator between each of them. Okay. And if you look at as time tends to infinity, what is happening, that eta d should track what the value of the reference which I have provided. So for a constant value of the reference, I expect as time tends to infinity, this thing to go back and start tracking that. Okay. Now, how fast it tracks or how slowly it tracks, does it have an overshoot and does it track, or does it track directly? These things will be governed by the damping and the natural frequencies, which I tend to choose and play around with. Everybody following me? Okay. This will be a little bit more clear when we start looking at the assignment for the guidance systems, which will be upcoming in this weekend. Okay. This weekend we'll have a assignment posted there, one for the modeling of the craft and the other one question of the guidance system. So at that time it will start making sense a little bit. Okay, so notice that so far what we have been looking at are so-called the linear reference models, right? These models are linear in case, which is why we are able to take a look at that so-called Laplace transform of it and deal with it, right? It's a linear system where the input linearly gets translated to an output, and the governing equation between them is a linear differential equation. We don't have any non-linearities present in the system so far. This is a very good way to go about it because it's very simple to implement and it doesn't take a lot of overhead. So if I'm actually implementing on a small craft like my scaled model, I might not be too worried about the computational aspects related with a simple filter like this. It'll be pretty straightforward to do the computation. But rather, if I had a very nonlinear filter or nonlinear kind of a way to figure out what the desired trajectory would be, then I'll be adding computational overhead onto my machine. Right? For very large ships where the computational powers are, you can have a real good computer on board, then these may not be a big issue. But if you're looking at the smaller sized vessels where, just like the ASV that we are building in our group, then we may be seeing that for that the computation is a bottleneck because we are using a Raspberry Pi as the main engine on it, so we can't overload it too much. So in this case, it makes sense to take a look at the so-called linear reference models in order to generate the desired path which we want to generate. Okay, making sense? Okay. Now notice that as the amplitude of that input from the joystick is changing, we will see that the behavior in the velocity and the accelerations and the higher order derivatives will be slightly different. You'll be seeing that the form may look the same, but their amplitudes will be higher as well. Right? But in a real scenario, when we are actually looking at a practical scenario, there will be certain limits to how much those accelerations can be, how much those velocities can be. I can't have infinite velocities or accelerations stem up in a real system. So it makes sense that when we are considering these systems, to make sure that it is capturing the so-called desired trajectory should not be in such a way where it is asking me to generate a velocity which is greater than what is possible. So for example, let us say, if it is asking me to generate a surge velocity which is equal to, let's say for my scale model, as it wants me to generate 5 meters per second. Okay, and the power required for that is, let's say, 1000 watts. I need a 1000-watt motor. But what I have on board is a 400-watt motor, then I will never be able to generate a speed of, or the acceleration required to generate that much amount of thrust to reach it. Even though my guidance system may say your desired value of velocity is 5 meters per second, I may never be able to actually get there because I don't have sufficient power. Right? So when we design these so-called guidance systems, the linear system works well, but then it doesn't have any bounds. If I give a much higher amplitude on the joystick, it may result in a much higher amplitude in the velocities, which may not be physically possible. So I have to kind of scale back. So when we start to understand this sort of a behavior, we may need to adjust the so-called weights of our filters depending on how high the amplitude is. I may say that up to certain amplitude, I'll go with certain damping ratios and certain natural frequencies. But if I'm giving much more higher amplitudes, I know that will result in an unphysical velocities and accelerations. So it makes sense for me to use higher dampings and different set of natural frequencies for those higher amplitudes. Okay, so that is one methodology to deal with the fact that the velocities and amplitudes which we are getting may not be commensurate with reality. Is that making sense? Yes, no? Yes, it is making sense. Can somebody summarize for me what did I say?
So the system will have limitations in terms of like the maximum acceleration that it can gain. But the guidance model can giving higher reference index. The guidance model can give out natural amounts of acceleration which cannot be given by the model itself. Like that much amount of thrust cannot be given by the ship. So in that case, like we'll have to for a limited amount of reference signal, we can give a mod expected omega and the damping. But for higher amounts of the reference signal, we have to give a higher damping or some different amounts of some different values of omega and damping in order to compensate for that.
Correct. So we will be changing the values of the gains of the filter. We'll be tuning the filter slightly differently when we receive higher amounts of the reference signal, and we'll be tuning the values differently for lower amounts of the reference signal. So that in both cases, more or less, the velocity constraints and the saturation constraints are matched. Right? Sometimes it might also be useful to actually include these saturations directly. We may want to include a saturation performance into our reference model, but please understand, the moment I add a saturation on any quantity, it's a nonlinear phenomenon. Okay, once a saturation is added, the system is no longer linear, because linear means that I have a linear variation with x, right? But when I say I am saturating it, I'm saying that beyond certain value, it will reach a constant value. Now, clearly that cannot be a linear system anymore, but still serves our purposes. If we wanted to do the reference trajectory calculation, we can saturate the inputs after we pass it through a linear filter and see what happens. Sometimes another methodology may be that let me add quadratic damping rather than linear damping in order to try to reduce my velocities and accelerations quickly down for higher values of velocities, because at lower values the quadratic damping will be low enough, but at higher values the quadratic damping will be strong enough in order to restrict my velocities and accelerations. So that might be another approach which I might use in the formulation of my desired trajectories. Okay, so the other approach might be to use nonlinear damping. Yeah.
Sir, we are using step inputs and all, right?
Mm-hmm.
Previously, we used step inputs and all for velocities.
Yeah.
So how do we know if the system is linear or not?
How do we know if the C system is linear or not?
Yes, because we are using step inputs and all, right?
The step input has nothing to do with linearity, no?
Sir, but the graph will be non-linear, right?
No.
For
We are
step
not
functions.
talking about whether the graph has to be linear or not. We're talking about whether the, what you call, okay, all right, I can see where your confusion is coming from. You're talking about this graph and you're confusing this with as the displacement versus time, right? I am not taking, this is not time on the x-axis. So let us say that I am looking at VDI, okay, as a function of VDI. So when I give the so-called reference value, okay, so when I give, let's say, RB as an input and I'm looking at VDI as the output, when we had previously, the steady state value would be the same, right? For a given RBI, for a given RB value, for a reference value which I give, as time tends to infinity, the velocity desired will reach the value of the reference which I provided. Correct? That's
Yes,
what
sir.
we had before, right? This is what we had.
Yes.
Right? As time tends to infinity, it will reach the same value. Then that is what it means linear. As I start giving bigger and bigger references, constant references, and I hold it, I would expect my velocity to reach that higher value and stabilize there. But what I'm saying is there is certain limitation to what is the maximum velocity which my craft can achieve. Right? So even though my reference may be bigger, my velocity might actually saturate. I may not be able to generate a high enough value. So you can think of it like this. As I move my joystick up, my speed increases, let us say. Okay? As my joystick I move up, different position of the joystick will result in a different steady state speed which the vehicle will achieve. Okay, but there is a limit beyond which even if I push the joystick further, there will be no significant increase in the speed, but the speed stabilizes. My motor is running at its maximum capacity. It cannot go any further more than that. It cannot generate any more power than that. Then that is what I am referring to as saturation. Okay, so wherever I am actually seeing that the output of the system is coming to be at this value, I'll say no, it can't be there, it has to be here at the same VD value. So I'm passing it through a first order filter, I'll get a velocity as an output and I say, oh okay, what is the velocity I got? It is less than the maximum velocity that I can achieve. Then I just keep it as is. Up till that portion it is linear. But if the velocity desired is coming out to be bigger than the velocity I can possibly achieve, then I saturate it and I say it is equal to the maximum value that I can get. In that sense, the system is no longer linear because as my reference now keeps increasing, my velocity doesn't keep increasing linearly. It only linearly increases up till it reaches that maximum velocity. any more than that, I still start giving more reference, it still stabilizes at the same velocity. You got my point now?
Yes, sir.
Okay, this is not a plot with time, and I think that is what was the confusion as to with step inputs.
Yes, sir.
Okay, so this is not a plot of it's a plot of the reference signal versus the desired value which we are getting. Okay, all right. Okay, maybe here might be a good, interesting. Just want to take a look at Mawson's this thing. Let me pull it up once again. Maybe we can take one of those MSS toolbox example. We can take a look at it. Give me a second for my MATLAB to load up. Example called XREF mode. This thing taking so long. This, are you able to read the legend on this? Possibly not, maybe, right? I think I have to share my screen, not an application. Are you able to read this legend? Yes, or it is too small?
A little small, but I think it's...
Okay, if it's a little small, we'll make it bigger. It's not a big deal. Okay, this must be a little better visible. Yes.
Yes.
I can't see you when I'm sharing my screen, so you have to help me out here.
Yes, sir.
All right. So in one case, we are basically trying to simulate the second order spring mass damper system. Okay. And in one case, we are providing a linear damping, which is the blue curve. Okay. And that gives us the so-called plot of the position. So the top plot is the plot for the position. The bottom plot is the plot for the velocity. Okay. So what it means is I'm looking at basically how does the position and the velocity of that so-called spring mass damper system vary when I provide a step input to the force. Okay, so when I provide a step input, you'll see that the velocity first shoots up almost to about 3.5 meters per second, 3.6 meters per second, and then it slowly comes down. Everybody with me so far?
Yes, sir.
Yes, but there may be potentially be that we may not be able to achieve these velocities in reality. So in which case we can augment the model slightly differently. So this dotted black line that you see is adding nonlinear damping to the spring mass damper system. So what it is doing, because of the nonlinear damping, now you see that the overshoot of the velocity is not as high. The velocity is now relatively lower. Yes? So what went to 3.6 now only I went to a maximum of maybe 2.3, right? Now, sometimes it may so happen that even that might not be achievable. That might not still be a velocity which physically represents the limits. And the velocity can no longer be more than 1 meter per second, let's say. In which case, we may want to saturate the model. And when we saturate the model, we are restricting the velocity to be maximum 1. It cannot be any more than 1. So you will see here that in each of these 3 cases, when the overshoot is being decreased, the system takes longer to stabilize into the steady state value. All of them reach the same steady state position of 10, but the one with the quadratic damping reaches there slower than the linear damping, and the one with the saturation reaches even more slower than compared to the quadratic damping case. In fact, if you look at the one with the saturation model, you'll see that it will be a straight line in the position. Because the velocity is constant, the displacement should increase linearly with time. Is that making sense? Yes? Okay, good. So that's the primary idea. So when we use that so-called linear reference model, it is relatively easy to compute, but we may have to augment it sometimes with these quadratic damping or with saturation inputs in order to make it a feasible trajectory which can be realized by the craft. So adding them will definitely be useful for generating these
Sir,
trajectories. Yes.
how do we know up to what value should we saturate the velocities? We need to know the physical limitations of our system. No?
So they basically come from your physical limitations of your. So, for example, let us say that I know what is the say for my craft. So for our craft, we know that the motor's rated power is 400 watts. Okay.
Yes.
We know how much thrust the propeller can generate at different speeds.
Yeah.
Correct? Based on that, we know what is the thrust value it can generate. We know what is the power. If I divide the power divided by the maximum thrust I can generate, I know what is the maximum velocity I can achieve.
Okay. Okay. So these kind of calculations will be done before and then yeah. Okay.
Correct. So these are like a back of the envelope calculations which we might want to do ahead of time in order to keep it. Even if say suppose this value, physically maximum value, I keep it slightly below the maximum velocity that I can physically achieve. There's no harm in it, right? The system can still work.
Yes. Yes.
So as long as I have an estimate for it and I'm a little under that value, it should be good enough.
Yes.
Any other queries so far? No other queries? Okay, good. So in that case, we'll come back to my thing. This is an example from MSS Toolbox. So you can actually run it on your own. You have to install MSS Toolbox. You have to basically download that repository and include it into a path. So I can just share with you where to do that in case if you're interested. So typically on your MATLAB screen, there will be something called preferences. Below that, there will be a thing called set path. So if you look at set path, then you can go ahead and add the so-called folder. So I click on add folder. So I go into wherever this thing is. So in my case, it is in research and GitHub, and I've put it here somewhere, MSS. Okay.
So actually, in the add-ons, we can directly do that. We just have to click one. We just have to give one click. It will do automatically.
Correct. You can do that way also.
Yeah.
Okay. I'm the old school guy. Okay. But yeah, you can definitely do it that way as well. So you add the path, basically clone the repository locally on your directory wherever you want, add the path to the system MATLAB path, and that should allow you to access the complete application toolbox. Okay. All right. Okay. So let me come back here. So we kind of looked at the ideas that if I wanted to generate a so-called reference trajectory, how would we generate the so-called reference trajectory for a graph for a given step inputs, which are coming from either joystick commands or keyboard commands. And what we have looked at right now is the so-called linear reference models. And we also saw that linear reference models may not be enough all the time, for which we may need to augment sometimes by the nonlinear damping or by saturation effects in order to reflect reality better. Now we look at a second methodology to derive these so-called desired trajectories out of the system. Okay, so when we looked at these linear models, we know that they're very simple to implement. So, and they're pretty straightforward to implement. Only thing which we have to typically keep in mind is that you should keep the cutoff frequency of the reference model must not exceed the closed loop bandwidth of the system. And that is quite difficult to verify practically, especially when you have nonlinearities in the system. For example, when you have saturations or quadratic damping, you can't always verify this straight away. But before I proceed further, I want to first understand what do I understand by this thing called closed loop bandwidth of the system. And because we really did not talk much about it, let me give it a brief talk about it here. Okay, so remember when I drew out the previous system, I had the guidance system, which was taking the input to the control system, which is giving it input to the plant, and the plant was being read by through the navigation system and providing a feedback in order to get the error signal, right? And this is where we give that so-called joystick or keyboard or some other methods of inputs to our system, correct? And then we basically convert this into a set of desired trajectories. So that is where you get the so-called desired trajectories, which then your control system, if it is doing a good job and you have a good navigation system which is able to measure back the sensors information properly, you expect the output here to be equal to eta d. Correct? You expect whatever I have given as the so-called desired trajectory for my system to follow. If my control system and navigation system are doing a good job, the output should be the desired trajectory which I wanted to follow. Is that making sense?
Yes, sir.
Yes. Now, what I'm going to say is for the sake of argument, I'll put all of this part, okay, as a single block. So I have a guidance system which is giving something to this block, which is giving me the so-called eta. I'm giving this fellow the eta desired, and that is giving me output as the eta. And if everything goes right, this should be equal to eta desired. Correct. So this big block that you're seeing there, that is what is called as the closed loop system. Right? It's a closed loop because there is a feedback from I'm pulling a feedback of the output and passing it back as an input, and I'm giving it as a negative feedback in this particular case. So that big blob is the so-called closed loop system. So I'll call this closed loop system. Now what's happening, that's closed loop system. When I want to give a reference trajectory and I want my closed loop system to follow that reference trajectory, let's now go back to the previous discussion about the transfer functions. Remember when we were looking at this so-called eta d, I wanted to look at its transfer function to be relatively flat up till some point, and then it kind of drops down. Right? Higher frequency stuff I did not want to have. I wanted to behave like a low pass filter. That was my guidance system. So this curve is basically representing my guidance system. What I'm saying here, the statement that the cutoff frequency for the reference model must not exceed the closed loop bandwidth of the system. Which means if my system's bandwidth, let's say if I'm looking at this closed loop system's transfer function, let's say that looks something like that. Is that a good thing or a bad thing? And why? If my closed loop system looks like this, closed loop system's transfer function looks like this, and the guidance module's transfer function looks like this, is this a good thing or a bad thing? What do you think? And here I'm trying to basically get you to think in these lines as a control engineer. Okay, this is less of a, it's more of an intuitive understanding which I want you to develop. Bandwidth means the range of frequencies at which the values are less than, the values are good enough, right? They're not very close to zero. Again, please make sure that I'm making sense here because I'm plotting this on the log scale. You're assuming that I'm plotting this in the log scale. Okay. All right. So if I'm assuming that I'm plotting this in the log scale, as the curve goes down, it means the signal is really getting attenuated. There's nothing which is coming out of there. That's what it means. Okay. Now, can you think and tell me what your thought process should be? Is this a good guidance system? If the closed loop system's transfer function looks like what I have drawn there, and the guidance system's transfer function looks like the one we have drawn there, is this a good guidance system? When is the guidance system good? When it gives out reference trajectories which can be actually tracked by the craft. That's when it's a good guidance system, right? Is that so in this particular case?
At zero frequency, the guidance system is saying that give more than what the closed loop can actually give.
At the zero frequency, it is more or less able to track, correct? Both are having good enough values, indicating that if I give a close to zero frequency trajectory, then the closed loop zero frequency trajectory can be tracked by the so-called closed loop system, can track the trajectory. I'm more interested in what is happening on the right hand side, Vallabh. Say suppose I give a trajectory at this location. with that frequency, which means that my trajectory, let's say in X and Y, is oscillating like that. And that frequency is mapped to here. Is that a trajectory which my craft can follow now?
No, sir.
Your craft cannot follow it because the craft's bandwidth is less than the guidance system's bandwidth.
Yes.
Is that making sense? The craft's bandwidth is less than the guidance system's bandwidth. So there is a portion of the bandwidth in the guidance system where I will generate a trajectory which really cannot be tracked by the craft.
Yes.
So in order to have a good guidance system, you want the bandwidth of the guidance system to be lower than the guidance system of the craft.
So I didn't understand, how did you say that this trajectory will not be achievable by the graph, the control, the closed loop system graph here?
Correct. Okay. So look at the point where I have drawn the straight line.
Yes.
Right? At that frequency, what will be the output of the plant? If I give a frequency of that signal as an input to the closed loop system, its output will be negligibly close to zero.
Okay. Okay.
Isn't it? Whereas if I were to draw a line here somewhere, let's say somewhere here. If I gave this frequency input to the closed loop system, then it will have a significant output, which means it's able to track it. Yes, it is scaling it up or down depending on the dynamics of the craft. I'm kind of not considering that, but at least I'll get back something as the output. But when I go further away to the right, I am not getting an output. It's coming close to zero. So if I give it signal of that frequency as an input, the craft will not give an output, basically. What does that mean? It means it's not tracking what I'm asking it to track, isn't it?
Yes.
So I want to make sure that what I want it to track is actually trackable in some sense. And it is only trackable wherever the transfer function is not close to zero. It has a significantly good value.
So up to the left, up to some left part of the line that you have drawn.
Correct. Right. So if I had a guidance system which looked somewhat like this, let's say, then that's a good guidance system because at least all the frequencies here can definitely be tracked by the craft.
If I give some higher frequencies, let's say, in that case, the guidance system will not produce any.
Correct. So you even though you may give higher amount of frequencies with your joystick, the guidance system itself is rejecting those frequencies and giving a signal which is low frequency enough, which actually can be tracked by the craft.
Yes.
The idea of the guidance system is what? It should generate a trajectory which can typically be followed by the craft.
Yes.
Right? So that has to ensure that the craft's bandwidth should always be more than the guidance system's bandwidth. Only then will the craft be able to follow whatever I'm asking it to track. Okay, I hope that point is now making sense.
Yes, sir.
Yes, sir.
So, and all of this is relevant when you are looking at linear models, because we are talking about frequency domain here, isn't it? All of this goes out of the window the moment I start putting non-linearities into my system, which is why the nonlinear control is a harder subject to follow up. Right? It is difficult to prove stability in those cases. But as far as linear systems are concerned, I can simply look at their transfer functions, figure out what is the bandwidth, and say that, okay, as long as the bandwidth of the craft is is more than the craft bandwidth of my guidance system, then the guidance system is doing a good job. It can generate trajectories which can typically be followed by my craft. Okay. I'm giving you a sense of these things because we are going to be talking more about these transfer functions as we come to control also, especially when we deal with linear part of the control. When you start dealing with nonlinear control, all of this goes out of the window because linearity doesn't hold. Frequency domain transformations no longer hold. So we'll have to come up with newer methodologies in order to satisfy the stability criteria. That is when we have to introduce something called Lyapunov theory. And we'll come to it as and when we progress further. Okay, at least I hope this part is now clear that whenever I have a bandwidth, the reference cutoff frequency of the reference model must not exceed the closed loop bandwidth of the system. But as I said, when you have nonlinearities, saturation included in your system, or you have time delays, which means that I gave some command, but the system actually doesn't respond until some few seconds later, then you don't know that the system is linear. When the system is no longer linear, this part of verification whether the closed loops bandwidth has no meaning anymore because you can't apply linear theory anymore. Okay, so take it with a pinch of salt. The idea is if the system is assumed to be linear and I can compute its bandwidth, and I have a guidance system which is also a linear reference model, I typically would like to have it designed in such a way that the so-called bandwidth of the guidance system should be less than the bandwidth of the control of the plan that I want to control. Okay, I hope that makes sense. Okay. Okay, so I'm seeing that it's already at 10:15. Rather than start the new concept about trajectory generation using a marine craft simulator, we'll stop here for today and we'll reconvene on Monday. Okay, it's better I do not bombard too much information. Let it sink in what we have discussed today, and we'll come back and hit the other part on Monday. Okay, so let me stop recording.